In this video, we derive by hand the gradient of mean squared error. We confirm that the partial derivatives we compute manually correspond to those calculated with automatic differentiation. And then we visualize gradient descent in action over rounds of training. In the preceding video, we began working through this batch regression gradient notebook. In it, we loaded in the data, we passed our x values, our 8x values, through a forward pass, so through our regression model, m times x plus b, to estimate what the output should be to generate these y hats. Then in step 2, we compared the y hats with the known y values, the correct values that we should be able to estimate with our model, and we calculated mean squared error, so corresponding to a quantitative difference between the estimated y hat and the true y value. Then in step 3, we used automatic differentiation to calculate the gradient of cost with respect to our model parameters m, the slope of the line, and b, the y-intercept of the line. Now, we've used Autodiff many times before to solve problems like this, to calculate the gradient of cost with respect to parameters. And once, a couple of videos ago, we also by hand calculated for quadratic cost the partial derivatives so that we could get the gradient of cost without Autodiff. So we manually calculated del C del M and del C del B for quadratic cost. Now we're going to go and do the same thing with mean squared error. Okay, so here is mean squared error. We've got our quadratic cost there, and then we sum up however many instances I we have, and we divide by n, the number of instances. So that's just an averaging of quadratic cost. That is mean squared error. Now, we can start off by calculating the partial derivatives of c with respect to y hat. So we're interested in ultimately getting the partial derivatives of cost with respect to the model parameters. Those model parameters are nested inside y hat. So on this slide, we're going to find mean squared error with respect to the predicted y. You can notice that mean squared error could be considered to be a nested function. So y hat minus y, I'm going to call that u. And then this is what the rest of mean squared error looks like. So if y hat minus y is u, then this is the same thing as here. But now we can calculate partial derivatives on these two separate simpler functions. So this is the simplest one of all. So del u, del y hat, this is the same, very similar to what we had in an earlier video where we calculated the gradient of quadratic cost. And so the math is similar. We want to differentiate u with respect to y hat. And in so doing, y is a constant. So it becomes 0. This entire term becomes 0. Y hat is really y hat to the power of 1. And so according to the power rule, it becomes 1 times y hat to the power of 0. And anything to the power of 0 becomes 1. So we're left with 1 times 1, and that's 1. We've seen that happen many times in these derivations of gradients, whether it's quadratic cost or mean squared error, it seems. So yeah, so that simplifies 1 minus 0 simplifies to 1. So del u, del y hat is equal to 1. All right, and now we have this equation over here. So let's calculate the partial derivative of cost with respect to u. So this whole thing up front, we can consider that to be a constant. And so we differentiate u squared according to the power rule. That becomes 2u to the power of 1, which is just 2u. And we can make this look a little neater by moving the 2 over here. It's exactly the same arithmetically, whether we have it before or after the sigma. And yeah, then once we have our nice expression here, we can drop y hat minus y back in for u, and that gives us del c del u. It's equal to 2 divided by n, and then sigma of y hat minus y. So there are our two main pieces of the puzzle for calculating the gradient of mean squared error. I've just rewritten them here on a new slide because now on this slide we're going to actually find the mean squared error, the partial derivative of mean squared error with respect to model parameters. But we're going to need the partial derivatives from the preceding slide. In addition, we're going to need these two partial derivatives which we already found earlier in the gradient of quadratic cost video that was earlier in this machine learning foundation series. So in the interest of time, I'm not going to redo that entire derivation again. But in summary, del y hat del m is equal to x, and del y hat b is equal to 1. So with these 4 partial derivatives, we can use the chain rule to calculate the partial derivative of mean squared error with respect to both of our model parameters, m and b. So let's start off with b, because the math is a little bit simpler, you'll see. So in order to get del c del b, we can chain together del c del u del y hat, and del y hat b, because del y hat and del y hat will cancel out, del u and del u will cancel out, and so we'll be left with just del c over del b, which is what we're looking for. It's the partial derivative of mean squared error of cost with respect to our model parameter b, the y-intercept of our model. So, knowing that we just need to perform this multiplication, chain together these partial derivatives, so we can just drop in. We've got del c del u first. The second one is del u del y hat, and that's just 1. And same thing for del y hat del b, it's just 1. So multiplying 1 times the rest of this, we're left with just this expression, which is actually also del c del u. But this is del c del b, so the partial derivative of mean squared error with respect to our regression model parameter b. For del c del m, it's a similar story. The first 2 partial derivatives are the same. And then the third one in our chain rule is del y hat del m, right? And now the del y hats will cancel out, the del u's will cancel out, and we'll be left with del c del m. So, substituting in those expressions, we have this one here again in front, del c del u. Again, del u del y hat is just 1. And finally, del y hat del m is x. So, simplifying this, the 1 disappears because, I think that should be pretty obvious. And so we're left with this here. So this is the partial derivative of cost with respect to our regression model parameter m. So there you go. We've done it all. The only thing that might look a little bit confusing here that I haven't talked about too much yet is how we have this I subscript all over the place here. And that doesn't mean very much. It just means that we're dealing with a single instance. So a single output y, a single estimate of y hat, a single input x. So, that distinguishes from how when we sum up all of the individual instances and then perform other operations on it. So there's when we're treating things just as individual instances as well as an average, and so those i's just make sure that we know when we're dealing with individual instances. Previously, when we were dealing with quadratic cost, we didn't need to specify individual instances because with quadratic cost, we were only ever dealing with individual instances, so that I would have been redundant and obvious. Okay, so now armed with our 2 partial derivatives, del c del b and del c del m, we can jump back into our hands-on code demo and confirm whether Autodiff gets the same values with real numbers as when we use our manual derivations of these partial derivatives. Okay, so when we used Autodiff to calculate the gradient of cost with respect to m, we got 36.3 as our value back in our batch regression gradient notebook. Now that we've derived del c del m from mean squared error cost, we can compare and see whether we get the same thing. So this is exactly the same as what we derived on the slides. And then here is some code that represents this mathematics. So we've got our y hats minus our y's. We multiply them by x's, by x, and then we sum up across all of those instances. And we multiply by 2 divided by however many instances we have, which happens to be 8. All right, so let's execute this code cell and see what we get. We get 36.305, exactly the same as we got with Autodiff in PyTorch. And how about del C del B? So with Autodiff, we got 6.3. And with our del C del B equation that we determined on the slides, here is the Python version of that. And so we can execute the code and boom, we get 6.265, exactly what we got with Autodiff. Nice. So hopefully now you've got a good working understanding of what it means to have partial derivatives of cost with respect to our model parameters. So, now we understand how to do it very quickly and easily using Autodiff and PyTorch, but you also understand what's happening under the hood by understanding the partial derivative calculus that's involved in calculating these components of the gradient. So speaking of the gradient, we don't need to explicitly create a standalone Nebula C object, but we will. We're going to. So we don't need to for the remainder of this notebook to run. So we don't need to create a gradient tensor, but we're going to create it for fun now anyway. And we will, in subject 8, the final subject of this Machine Learning Foundation series, we will make use of this Nebula C object, this gradient. And so we might as well create it now while we're talking about it, while we're on the subject, and to reinforce the understanding of what a gradient is. Yeah, and we'll come back to this later on, right at the end of the Machine Learning Foundation series. So just as in an earlier notebook, the single point regression notebook, we take our individual partial derivatives of cost with respect to the model parameters. So I'm putting them in alphabetical order. So we've got del C del B here and del C del M here. We put them all together in a vector, and then we transpose the vector so that it's a column vector. That's the convention with gradients. And so there you go. There's our Nebula C object, our gradient. All right, so having done that just for fun and for something useful later and for reinforcing, let's get back to kind of the main point of this notebook. And let's now see gradient descent in action. So in order to see that effectively, let's visualize all of the most pertinent metrics in a single plot. So I'm calling this a labeled regression plot function. And so we pass in our X, our Y, our M parameter, our slope for our model, our B parameter, the y-intercept for the model. We pass in our cost. And then we also have this option to include the gradient or not. So in some situations, I want to output extra information about del C del B and del C del M. Other times it won't make sense to show it. So that's an argument. By default, we will show it, but sometimes we'll turn it off. So yeah, so we've got some handy things to make understanding the chart easier. We give it a title with the cost in it, summarizing the cost. We also give the chart an x-axis label and a y-axis label that contains information on the M and B parameter respectively. And yeah, we plot things out. We just put our x and y values in a scatter plot, and we use our regression function to plot out a line. So running from our lowest x value, that gives us the corresponding y value for the starting point of our line. And then that line, that regression line, will run to x max and the corresponding y max value, in both cases based on our whatever our m and b parameters are at the time that we call this function. Nice, so that's about it. These are just related to making sure that the plot looks nice and that we get our line plotted out. So let's make sure we run that. And then here, let's see what it looks like. So all of my explanation of what's in there probably would have been easier to understand if I had already just plotted it out. So here, we're getting our training data points, our x and y values, and then prior to having done any training, this is where our regression line sits. So this is based on the quote unquote randomly initialized values that we started off with, which is a slope of 0.9 and a y-intercept of 0.1. So that's where we intersect 0 here. All right, and we've got our partial derivatives shown here as well. So we've got del C del M, which is equal to 36.3, and del C del B, which is equal to 6.26. So these are the values that we've now calculated both with Autodiff as well as with our manual calculations. So that was a very long-winded step 3 in which we determined those partial derivatives. So now step 4 is to actually descend the gradient now that we have our gradient. So the del C del M part of our gradient, which is equal to 36.3, this indicates that an increase in M corresponds to a large increase in C. So there's a positive correlation between M and C. Meanwhile, del C del B being equal to 6.26, this indicates that an increase in B also corresponds to an increase in cost, though much less so than M. So the magnitude of this, that this is so much a larger value, means that making a big adjustment. So in the first round of training, the lowest hanging fruit based on these two values with respect to reducing cost C is to decrease the slope of the regression line M, because decreasing M is going to make a big difference on decreasing C. We can see that they're positively correlated, and we can see that, there's this big slope there. So there will also be a relatively small decrease in B in the y-intercept of the line. So in either case, because these are positive values, we know that there's a positive relationship between cost and the parameter. And so reducing that parameter value somewhat is going to reduce cost in either case. But because this del C del M value is so much bigger, there will be a relatively small decrease in B relative to M. So the exact details of the mathematics of gradient descent that we're going to cover in full detail in Subject 8 on optimization, the final subject of this Machine Learning Foundation series. In the meantime, we're going to continue to use the PyTorch stochastic gradient descent optimizer. So we've used this before in several earlier notebooks in this Machine Learning Foundation series. The first argument, we pass in a list of the model parameters that we would like to adjust, in this case, M and B. And we also provide a learning rate, which is how much to adjust M and B. Again, in Subject 8, we will get into a huge amount of detail as to what learning rate is. But for now, you can trust that this value of 0.01 is pretty good for training this particular model with these particular data points. So this initializes our optimizer, and then with a call to the step method of the optimizer, that actually performs gradient descent. So this optimizer goes to whichever parameters we told it to go to, and based on the gradients, based on the partial derivatives of cost with respect to those parameters, it adjusts the parameters, both of them, M and B, according to the kind of high-level explanation that I provided here. And to confirm that that worked, we can now perform steps 1 and 2 of our 4-step machine learning process again. So step 1 is the forward pass, and then step 2 is the calculation of cost using mean squared error in this case. And let's replot everything again now. And we see, yep, our cost is much lower than before. So it was almost 20. Now it's 8.5. And our slope has been lowered quite a bit. So it went from 0.9 down to 0.5. And our y-intercept also has been lowered, though not as much, for the arguments that we talked about here, but it's gone down from 0.1 to 0.04. So now we can just rinse and repeat. So let's look at 8 more rounds of training on all of our training data. A round of training on all of your training data is called an epoch. And so in each round of training, in each epoch, we will start off by zeroing out our gradients, otherwise they accumulate and needlessly take up memory in this case. And then we do step 1, the forward pass. Step 2, we calculate cost using mean squared error. Step 3, we perform automatic differentiation. If you wanted to, you could now actually use the manual derivations that we determined here. You could create functions for these, and instead of relying on Autodiff, you could use those. But this was the easiest and simplest thing to do, so I did it. I just used the backward method yet again, used Autodiff, and then I'm going to plot out kind of the state of play at that point, and then finally perform gradient descent. So let's run those 8 rounds of training and see how it looks. So the first output here, this is the same situation as here, but now I've also gone and recalculated the gradients. So I'm including the gradients now here as well. And you can see that the gradients are now not as steep. So the partial derivative of cost with respect to m, it was previously all the way up at 36. And because we've made an adjustment and the line is now fitting the data better, the steepness upon this particular direction of the gradient is less steep, though there's still a lot of room for improvement with respect to m, for sure. And same thing with b, it's gone down a bit. So going a bit further, by the next round of training, our cost has gone down further, m has decreased again, and so has the y-intercept b, and so have our gradients. And this trend continues. So our cost keeps going down, which is great. That's what we want. And at this point here, for the first time, we have a negative y-intercept, and we also have a negative relationship between cost and b. So this means for the first time in this notebook that a reduction in b would actually increase cost. So we want to increase b, and that will correspond to a reduction in cost. So that's what the negative sign there means. Yeah, and so our y-intercept moves up a little bit as opposed to going down. And yeah, this continues to correspond to lower and lower cost as the slope and the y-intercept of our regression line continues to fit the data points better and better and better. So yeah, I already talked about this inverse relationship, and you can continue to run this if you want to. Because you're generating plots every time, it starts to get a little bit difficult on the RAM on your machine if you were to run this, say, 1,000 times with the plot coming out. But you could comment out this line of code, and then you could run this as many times as you like. If you run it 1,000 times, then your regression line, your model parameters are going to fit the data points very, very well by that point. And then you could consider running this plot one more time. And if you did that, if you did run for 1,000 more lines of training and output the plot, you would end up with something that looks exactly like this, a plot that should look identical to this, where, yeah, we can see our cost is very low, very close to zero, probably as low as it possibly could be given the noise in our data that these, a line could never fit these data points perfectly. And yeah, we can see that our gradient del C del M has become very close to zero, as well as our gradient del C del B, indicating that we have probably found, we're getting very close anyway, to the perfect point in our cost curve. We have minimized cost with respect to both of our model parameters. All right, and so what are our parameter values? Well, just as in earlier notebooks where we solved this same problem using the same approach, though to not nearly the same level as detail as we did now, we get the same result. We get a y-intercept, a b of 1.75, and a slope of our line of negative 0.468. Wow, what a video. Hopefully all of the pieces are now starting to fall into place for you, that you can see not only how partial derivatives make up the gradient of cost, but also how the core essence of most machine learning approaches is descending that gradient by tuning our model parameters. To be sure not to miss the next video in this series, subscribe to my channel. Thanks for taking part in this tutorial. I hope you enjoyed it. If you did, please like and comment. To be sure not to miss any of my content, head to jonkrohn.com and sign up for my email newsletter. You're also welcome to add me on LinkedIn. Simply mention that you're a viewer of the Machine Learning Foundation series. And finally, you can follow me on Twitter too if that's your social medium of choice.